So let's look at the shape of d orbitals. That's what we're doing next. In transition elements, we had seen earlier the physical properties and atomic properties of different transition metals within each other and how they also compare to group 2. Now we're going to talk about the chemical properties of transition elements. And to do that, we have to understand their d orbital structure. For that, we have to talk about the shape of d orbitals. In AS level, you do the shape of s orbital and you study the shape of the p orbitals, the three of them. But at the d sub level, you know there are 5 d orbitals, but we don't study the shape of the d orbitals. And the first sub level, or the first, energy level that we encounter, the d sub level, is the 3d sub level, or the third energy level. So we are going to focus our attention mainly on the 3d, but it applies to all d sub levels. Now, one thing that's going to be very, very important is, so that there are 5 d orbitals at any d sublevel. That's the first thing, and you know that's from AS level. Now, the 5d orbitals in any d sublevel are divided into 2 different groups. They're literally divided into 2 different groups. So the 5d orbitals are divided into a 3 orbital group, literally that, and a 2 orbital group. And that has to do with the shape and spatial arrangement, like how they are occupying space around the nucleus. So we have a 3 orbital group and we have a 2 orbital group. And these orbitals have very weird labels. Like if you remember, the p orbitals had labels like px, py, pz, and that the px would be along the x-axis, the py along the y-axis, pz along the z-axis. Now, that was easy labeling. S, since there's only 1 orbital in each sublevel, there's only that label. But before I show you the shapes of the 3D orbitals, know that the names are very funky also. So 3 orbital groups, meaning the 3 orbitals part of the 3 orbital group are dxy as subscript, dxz as subscript, and dyz. These are our labels given to 3 different orbitals: dxy, dxz, and dyz. And I'll show you why they are that. But the other 2 orbital groups are the x² minus y² is given one label to one axis, one d orbital, and the other d orbital is dz². And these are just our ways of labeling some. And I'll explain to you why. You can kind of figure out why, but you should be able to recognize that just like the p, x, y, and z, d5 orbitals have different labels. There's a dxy, there's a dxz, yz, x² minus y², and z². And the squares are one set of orbitals. They are similar in their nature. And the xy, xz, and yz are the 3 orbital group, also have some similarities among themselves. And later on, when we do color, when we do that part about it, these will come in handy, the division between 3 orbital group and a 2 orbital group. But even the shapes are also, or their space arrangements are determined by their names, or the names are determined by the arrangement in space. So let's look at some shapes of the 3D orbitals. So before I show you the shapes, one way to recognize which orbitals are the 3 orbital group are basically their space, or the occupants of space in relation to the axes. The 3 orbital group, the 3 orbitals in the 3 orbital group are all orbitals that lie between the axes. And the 2 orbital group are those orbitals that lie along the axes. And when I show that to you, you can recognize, and I'll explain that also. But let me just show that to you. This is taken from your slides, just pasting it in your notes. This might even be orange color. They look better in orange, but this is black background, so they're blued now. These are your 5d orbitals. This is, in fact, these 4 lobes make up one orbital. First, let's focus on the first one. Like you can recognize there are 4 lobes that make up one of the d orbitals. The same 4 lobes make up another d orbital here. 4 lobes make up another d orbital here. And then 4 lobes make it right here. And this one is actually 2 lobes and a donut with it. It's the only one that's a unique shape. So 4 of them have the same shape and one of them has a different shape. Now they're also labeled in sets of 3 and 2 because the above 3 are the 3 orbital group, and this is the 3 orbital group. And what are they? They are the ones that lie between axes. Now what do I mean by when I lie between axes? It's easier for me to draw it to you separately, especially the fact that it's not very obvious here. So let me draw it out for you and then go back to there. When I say something is between axes and something is along axis, what I literally mean is this. It's also given in your notes. I'll go back to this picture that we just saw earlier in a minute. I'm just pasting the other diagram. The differentiation between what it means to be lying along the axis versus between the axis. And for that, I'm going to take the dx² example and the x²-y² example. And the reason why I want to take that is because those involve the same axes. So dxy versus the x²-y². They are both different types of orbitals. I'm just pasting their diagram right now, 1 second. And then I'll just show it to you, 1 second. So let me scroll down. Here it is. So this is the 2 orbitals. One set is labeled dx²-y². One set is labeled dxy. The xy's are the 3 orbital group. The x²-y² is the 2 orbital group. But what makes them different is because both of these have 4 lobes. The xy has the 4 lobes within the 4 quadrants, meaning they are lying between the axes. This can be considered the x-axis, the y-axis, the x-axis, the y-axis. So if you consider them, then the xy's lobes are going to be in all the 4 quadrants of the xy axis, while x²-y² will be that orbital where the lobes will lie on the x-axis and on the y-axis. That is the difference between lying between the axes. Between the axes means within the quadrant, and then along the axes, meaning the ones that lie literally along the line y and along the line x. And they are both in the same space together. So for an atom, if this is the nucleus, this space versus these 4 are all the spaces the xy electron will be at. Then the 4 lobes on the x and the y is what your other electrons can be at. So these are obviously existing simultaneously. And remember, what are orbitals? Orbitals are just spaces where we're going to find the electrons. Now, I'll go back to this diagram in a minute. I'll go back to the other one first. So what I was saying was there are 2 sets of orbital groups. Between the axes. So these guys are between the axes. And the last 2 are along the axes. Now, if you can figure out the x²-y² made, the lobes will be on x and y. They have made x and y this way. And z² will be along the z-axis and a donut around the z-axis. So this is what we have calculated and proven this arrangement or the space electrons can occupy if they are on the d sublevel. Hence the name d orbital. So for you guys, for the exam, you need to know this. There are 3 orbital group and a 2 orbital group. The 3 orbital group are when the 3 orbitals have each one having 4 lobes, and each of those 4 lobes lies between the axes. And the ones that lie along the axis are the 2 orbital group, and one orbital's 4 lobes lie on the x and the y, and the other ones lie on the z. Now here, if I go back to this could be xy. If this was x and z, this would be xz. If this was y and z, this would be yz, no matter how axis you make. But x²-y² will be this way, and z² will be exactly along the z-axis. So you literally have 5 orbitals, and you will be asked to draw them in the exam. There are enough questions to ask you to try the 2 types of orbitals. So what I tell my kids is this: if you're asked to draw the 2 types of orbitals, draw one xy like I just did and one z², because z²'s shape is different and it's also along the z-axis. But if you don't want to draw the z and you want to draw the same shape, then you draw this. You literally draw the axes. This is me writing 45. It's like taking these orbitals and rotating the orbital 45 degrees, and you'll get this. But these are the two different types of orbitals: between axes, along axes.